What's up, guys? It's Mr. Gaines again here, working on another section of the QF.2 notes for Algebra 2, taking a look at quadratic functions and graphs. The only thing that we have left to do is covering some application problems, and we got cut off a little bit on the timing of the last video, so I want to make sure that we go ahead and complete the last two problems. So let's go ahead and jump all the way down to problem number 7. In problem number 7, it says, in 1976, Pro Bowl NFL punter Ray Guy of the Oakland Raiders kicked the ball so high it hit the scoreboard hanging from the roof of the New Orleans Superdome. If h of t represents the height of the football in feet after t seconds, the function h of t, which it gives us there, models the relationship time to height of ball. So what it's telling us right now is that we have the scenario, Ray Guy kicked the ball, it hit the scoreboard. This h of t represents the time as the x-coordinate, or t, in relation to the height, how high the ball is after that amount of time. So in problem A, it says, what does the y-intercept of this function mean? So first, we probably want to identify what the y-intercept is. So remember that the y-intercept is when the x value, or in this case t, is 0. So it would be h of 0, which is going to be 1. We can substitute in 0 for t. We'd be left with just the constant. So h of 0 is 1. What does the y-intercept mean? This means that the ball will be 1 foot above the ground after 0 seconds, or the ball is 1 foot above the ground when it is kicked. So time starts when he's kicking the ball. So 0 would be the time of impact, and that ball would be 1 foot above the ground. It says, after how many seconds did the football reach its maximum height? So here we have, again, a question that deals with a graph. So what I'm going to go ahead and do is I'm going to type this function into my graphing calculator. You could do this algebraically. Again, if you want to find the algebraic solution to this, how many seconds would be time, which is the x-coordinate, which you can find using the vertex formula. If you want to do it algebraically, that's okay. I'm going to go ahead and do this graphically. So I'm going to sketch in, I'm going to type in my graph here. I'm going to go to zoom and window and set my x minimum to 0, because I'm not going to have any time less than 0. I'm going to set my x maximum to, I don't know, maybe, let's just leave it at 10 and see what happens. And I'm going to hit zoom, or second, sorry. And I'm going to hit zoom, go down to zoom 0, which is zoom fit, and take a look at my graph. So in here, I can see this is where the ball takes off at 0 seconds, and back there is when it reaches the x-axis. Remember, the y-axis here is height. So anything below the x-axis would be negative height. So I don't really need any of this section of the graph. You don't have to, but I'm going to cut my window down a little bit. Let's make this between 0 and 6. And now let me go ahead and take a look at my window, clicking zoom 0. I'm going to make it a little bit wider. So I'm hitting window, making my max 7, and then I'm going to fit the graph, because I want to make sure that I see where it returns to the x-axis. I want to see where it's getting back to the ground, potentially. So here's my graph. I'm going to go ahead and sketch this graph. And there I have it. I have just a generalized sketch for my graph. I have some labels for my axes here. And I've got my curve kind of representing what I see in the picture, okay? It's not perfect, but we get the idea. So again, the question we wanted to answer in B was, after how many seconds did the football reach its maximum height? So the purpose of this graph, or what I'm looking for on this graph, is the maximum point on the graph, the relative maximum. So I'm looking for this location. Again, I can find that algebraically using the vertex formula, because we know the vertex is going to be the maximum point. That's the turning point of the graph, the relative maximum. Or I can use my graphing calculator. So I'm going to hit second, trace, go down to maximum, which is 4. The left bound, I'm going to make sure I'm on the left side of this maximum point. For right bound, I'm going to go ahead and make sure my cursor is on the right side of this maximum point. I'm not even going to worry about guessing. I'm just going to hit enter, and there it's going to give me my maximum. So again, notice that it did kind of slightly round this. So my maximum is at 3,199. So I've labeled this point there, and basically that's my work. Okay, so if you did this algebraically, you'd show your steps, you'd show your algebraic use of the vertex formula, and that's fine. You find out the vertex is 3,199. So now I can answer B. It says, after how many seconds did the football reach its maximum height? My x-axis is time in seconds. My x value is 3. So it took 3 seconds to reach max height. You just said 3 seconds. That's okay. I can also use this point to answer question C. It says C was, what was the maximum height of this kick? Well, height is the y value, so the maximum height is going to be the y value at this location. So the max height is 199 feet. So once I use that, find that point graphically, I can use that point to answer 2 questions. Now, if you did this algebraically, you'd use the equation for h equal negative b over 2a to solve for the maximum height, and then you'd substitute that number into the equation to solve, or sorry, you'd use the h equals negative b over 2a to find the seconds that it takes to get to max height. Then you take that value 3 and substitute it into the equation to find the max height. In D, it says to the nearest hundredth of a second, how long was the ball in the air? So now this is a question that's branched out a little bit. This question is not going to have anything to do with the maximum height. It wants to know how long was the ball in the air to the nearest hundredth of a second. So really what we're trying to find is how long did it take for the ball to start here and return all the way to there on the x-axis. This is where the height is 0 on the x-axis. And that's going to be where the ball hits the ground. And it has no height, it's on the ground. So what I could do if I wanted to, algebraically, I could set this equation equal to 0. So negative 22t squared, or negative 222t squared plus 132t plus 1 equals 0. And then solve that. I'd likely want to use the quadratic formula there. But I can also use my graphing calculator. So this is going to be a lot easier if you have the graphing calculator, because I don't have to do near as much work. What I want to find is this location where it hits the x-axis. So I can do that by hitting second, trace, and going back to the calculate menu. This time I want to find the x-intercept. Another word for x-intercept is 0. So I can select the second option. Again, I'm going to see this left bound command on the calculator. So what I want to do is move my cursor over so that it is left of the x-intercept. It's left of the x-intercept here. I'm going to hit enter. Then I want to move my cursor until it's right of the x-intercept. I'm going to hit enter. It's going to ask me to guess. I'm not going to worry about guessing. And there's my solution. Okay. So it does say round to the nearest hundredth of a second. So we want to make sure that we round this appropriately. So I'm going to go ahead. My work here is going to be the point. I'm going to draw on my graph. I'm going to draw a point there. And I'm going to go ahead and label this point. So I went ahead and labeled this point. I rounded that answer to 6.01 because it wanted rounded to the nearest hundredth, and then 0 would be the height. So again, you could do this algebraically, but this is a lot less work. It said to the nearest hundredth of a second, how long was the ball in the air? 6.01 seconds. So if you want to write that in a sentence, that's okay. 6.101 seconds was the time spent in the air. And there we have solutions to these questions. Graphing. Again, algebraic is okay. If you like doing the algebraic work, that's fine. You would just make sure that you include your work there. Instead of drawing a graph, you do your algebraic steps. Let's go ahead and take a look at one more example. This example is a little bit more complicated. So in problem number 8, it says a theater decided to sell special event tickets at $10 per ticket to benefit a local charity. The theater can seat up to 1,000 people, and the manager of the theater expects to be able to sell all 1,000 seats for the event. To maximize the revenue for this event, a research company volunteered to do a survey to find out whether the price of each ticket would be increased without losing revenue. The results showed that for each $1 ticket each $1 increase in ticket price, 20 fewer tickets will be sold. So there's a lot of information that's going to go on here. Eventually, we want to talk about how to maximize revenue for this theater. So we need to get there first. We don't have any equation, we just have information. In the previous two problems, they gave us an equation. Now we have to develop an equation based on the information they gave us. So in B, it gives us some steps on how to get there. So let X represent the number of $1 ticket price increases. Write an expression to represent the expected price for each ticket. So let's let P of X be the price for the ticket. Okay, I chose P because P is short for price. So initially the price, what do we know about the price? Initially it was $10. So we're going to let this be in dollars. So the initial price was 10. But it says that we're going to increase the tickets by $1. By $1, excuse me. We don't know how many times we're going to do that, but we're going to increase it by 1. And then we may increase it by another 1. And we may increase it by another 1. So how we can represent this is we know that we are going to add 1. We don't know how many times we're going to add 1. So we're going to let that be X. X represents the number of $1 ticket price increases. So P of X could be 10 plus 1X or just 10 plus X. So the original cost was 10, and then we're adding $1 X amount of times. We don't know how many times we are, but we're going to. So we're going to change that price. It says use the survey results to write an expression represent the possible number of tickets sold. Well, let's let another equation, let's let S of X equal sold. S for sold in respect to X number of price increases. So initially, what does it tell us about selling? The manager expects to be able to sell all 1,000 seats. So initially they're going to do 1,000. But every time we increase a ticket price, every time we bump it up by $1, 20 less tickets are going to be sold. So for every ticket price X, we're going to lose 20 sales. So this is going to be 1,000, our initial amount, minus 20 for every time we increase $1. Now this next part, C, relies on some information that we've talked about but haven't really went in depth. And so this is an equation that you see pretty commonly in business. If any of you guys are going to go on into accounting or QBA statistics and any of that route in the future, you're going to use this concept and this equation pretty often. So revenue is equal to the price times the sales. So if we want to find R of X, let's speed this over a little bit. If we want to find R of X is our revenue. R stands for revenue. It's going to be equal to P of X, our price, times S of X, our sales. So the question does tell us to write R of X in standard form. So what I'm going to do here then is substitute in what we know about these equations. Adjust this a little bit so I have a little more room. Go. So then R of X is equal to our equation P of X, which is 10 plus X, times our equation S of X, which is 1,000 minus 20X. Now this is an equation for revenue. It's the price times the sales, but it asks for standard form, which means we need to simplify. We need to multiply this. So I'm going to distribute. I'm going to take 10 times 1,000. So 10 times 1,000 is 10,000. So I distribute the 10 to the 1,000. Now I'm taking the 10 to the negative 20x, which would be negative 200x. Now I'm going to distribute my x. X times 1,000 would be 1,000x. And then x times negative 20x would be negative 20x squared. So my equation for this, and we're not going to simplify, or we're not going to factor anything. We're just going to go ahead and write it in standard form. My equation for revenue is now equal to, I'm going to put it in standard form, so x squared comes first, negative 20x squared. I'm going to combine my 1,000x with my negative 200x to give me plus 800x. And then I'm going to add my 10,000 as my constant at the end. So this is the equation that represents the revenue for this business. So we found out an equation for price. We found an equation for sales. Then we multiplied price times sales to come up with revenue. And I went ahead and highlighted this equation because this equation is what we're going to use to move forward. So now it says, how many $1 ticket prices will produce the maximum revenue? In other words, what value for X produces the maximum R value? So this goes back to the graph, the function of the graph, or the graph of the function, sorry. So I'm going to go ahead and sketch out my graph. Negative 20x squared plus 800x plus 10,000. I'm going to set my window. I'm going to let my X minimum be 0 because I'm not decreasing the price so far. It's just what we don't assume we're decreasing the price. Let's let my X maximum be 10. I know that if I increase the price 10 times, now the price is 0, so the tickets would be free. So I'm just going to let it be 10 for the most that we could get to. So now I'm going to hit zoom. I'm going to go down to 0, zoom 0, zoom fit, and I'm going to take a look at my graph. Sorry, I explained that a little incorrectly. This is price increases, not decreases. So let's go a little bit beyond 10. Let's go to 20. Let's see what it looks like when it's at 20. We know what we need is we need to be able to see the vertex of the graph. So I see here that, okay, I'm pretty close when I'm at 20. I'm going to go ahead and let's double that. Let's make this 40. Make my X maximum 40, and there I can see a pretty good respect to the curve. Now, I often like to see the y-axis, so I'm actually going to come down here and I'm going to set my y minimum to 0, and now I'm going to graph this. I like to see the y or the x-axis where the x-axis is at. So let me go ahead and extend this. I'm going to extend this a little bit more. Let's make this 60. 40 would have been sufficient. 60 would have been okay. And then I'm going to set my y maximum or my y minimum again back to 0. And there I have a pretty good graph. I'm just manipulating the graph to get a good picture that I like to see. You don't have to do that much alteration. As long as you can see the vertex, you can answer question D. So now let's sketch the graph. And there we have an example for the graph. Okay, so this is similar to what I see there on my calculator. Not exactly. I went ahead and I labeled out on my window, my X minimum was 0, my X maximum was 60. So I went ahead and put that into my graph as well. I didn't put a maximum on the Y value because we're going to see that here when we graph that. So, or when we work on a problem with that one. Okay, so now we can get to asking or answering the question for D. Notice again that I labeled axes. My X or my Y axis is revenue, R of X. Remember, they told us what X was. They said X represents the number of $1 price per ticket increases. So I went ahead and labeled this a number of price increases, and we'll talk about solutions for that and labeling when we get there. It says how many $1 ticket prices will produce the maximum revenue. So here I have revenue. On the Y, I want the highest value on Y. So I want that point at the top of the curve. So I'm going to go ahead and mark a point here. and then I'm going to find that value. So I'm going to hit second, trace. Again, you could do this algebraically if you like, but I'm going to use my calculator, go down to maximum, move my cursor over to the left side of the curve, hit enter. Now it says right bound, move it to the right side of that peak of that curve, hit enter. It's going to guess. Ask me to guess. I'm not going to guess. I'm just going to go ahead and use the value that it's there. So it gives me X is 20, Y is 18,000. So I want to make sure that I label this point as part of my work. So there I have my point 20, 18,000. I'm ready to answer the question. So the question said, how many $1 ticket price increases should there be? There should be, that again is the X coordinate. So there should be, to maximize revenue, 20 price increases to maximize revenue. And 20 price increases would be sufficient. It says, what is the price of the ticket that will produce maximum revenue? So if I look at this graph, nothing here says price. I have revenue on my y-axis. I have price increases on my x-axis. To come up with price, I need to go back to my P of X equation. P of X is price. So really what I know is that I need 20 price increases. So my X value is 20. I want to know what my price is. So what I can do is I can find P of 20. Sorry. So P of 20 is really what we're trying to find here. And we can go back and we can pull from that equation. That equation is 10 plus X, so 10 plus 20, which would be 30. So what I need is a $30 ticket, or I need a value of $30, a price, $30 per ticket to maximize revenue. So once I had that revenue equation, I can figure out how many price increases would give me maximum revenue, and now I can adjust my ticket price to make sure I meet that maximum revenue. F says, what is the maximum revenue? So now I can go back to my graph. This information is located on the graph. So revenue is the y-axis on the graph, which would correspond to this point, the highest value. The y value there is 18,000. I want to make sure I put in units. So my revenue is $18,000. Again, we want to make sure we add some context there. It says, how many tickets will the theater need to sell to reach the maximum revenue? Going back over to my graph says nothing about sales. But I do have an equation up here that does tell me about sales. S of X is the sales with respect to X number of price increases. So maximize revenue is 20 price increases. So in this case, I need to find S of 20. So we can do this algebraically if you want. The calculator is an okay source to use as well here. So I would do 1,000, if you need to use the calculator, minus 20 times 20 to get a total of 600 sales to maximize revenue. Finally, it says, how much more will the theater make for the charity by using the results of the survey to price the tickets than they would have had they sold the tickets for their original $10 price? So we know what maximum revenue is. The revenue right here is $18,000. What we also want to figure out is, what is the revenue if we make no change to ticket price? Well, remember the x-axis here is number of ticket prices. If I make no change to that, that is what would be my y-intercept. My y-intercept, if I go back to the equation, is $10,000. So what I want to find essentially is I want to take R of 20, revenue with result after 20 increases, and subtract that by R of 0. So what is my maximum revenue? Minus what is my revenue if I make no change? So my maximum revenue, again, we already found this value, would be $18,000. My revenue if I made no change, would be the Y-intercept, $10,000. And the difference of these two things would be $8,000. So to answer the question, how much more will a theater make? So $8,000 more. So in this scenario, we had a lot more work to do. We had to establish an equation from revenue. In order to create a revenue equation, we need price times sales. So we used the information that was given to us to create an equation for price and an equation for sales. We combined those two equations into a singular equation for revenue. Then we were able to answer some questions based on generating maximum revenue. Now, in some instances, we did have to go back to the price equation. We did have to go back to the sales equation to get more information about specifically price and sales. Okay? So this is the conclusion of the QF2 notes. We have gone through graphing quadratics, their key features. We've gone through transformations of quadratics and how to use those to graph. We've talked about rewriting standard form into vertex form using the completing the square method, and also finding the vertex of an equation using the vertex formula. Finally, we looked at some applications, which is the real purpose of doing all of this work with graphing functions. Now, again, with application problems, you can solve each of these algebraically if you'd like. You would include your work there. If you want to do them graphically, because it's a little bit quicker sometimes and a little bit easier sometimes, you can go ahead and sketch out your graph as your evidence, your support for your answers, and then you can include those answers based on those graphical solutions. This is a good place to go ahead and end, as we have completed QF2 notes. We will have an opportunity to ask some questions over notes and go over homework questions the next time that we reconvene in class. As always, guys, thank you guys for tuning in, and I'll see you soon.